Good to see you. This final outcome tackles spread head-on, building up the standard deviation from scratch and then using it to unlock the normal distribution, the famous bell curve behind so much of statistics. An average on its own only tells half the story. We also need to know how spread out the data is. The range, highest minus lowest, is quick but hangs entirely on the two extreme values. The interquartile range is better, covering the middle 50% and ignoring the extremes. But the star measure is the standard deviation because it uses every single value to tell us, on average, how far the data sits from the mean. 3 linked ideas build up the standard deviation. A deviation is simply how far a value lies from the mean, x minus x bar. The variance is the mean of those deviations once we've squared them, the sum of x minus x bar squared over n. And the standard deviation is the square root of the variance, which conveniently brings us back to the original units. For a whole population, we label it with the Greek letter sigma. For a plain list of values, the standard deviation is the square root of the sum of x minus x bar squared, all over n. The routine is 4 steps. Find the mean x bar, then find each deviation and square it, then average those squared deviations to get the variance, and finally take the square root to get back to the original units. Squaring is the clever bit. It strips out the negative signs, so positive and negative deviations don't simply cancel each other out. Let's lay the method out cleanly. First the mean, add the values, and divide by n. Second, the deviations, subtract the mean from each value. Third, square each deviation and total them up. And fourth, divide that total by n for the variance, then take the square root for the standard deviation. Let's do a real one. 6 days of sales in hundreds of pounds, 6, 8, 9, 11, 12, and 14. The mean is 60 over 6, which is 10, so £1,000 a day. Squaring each deviation and totaling gives the sum of x minus x bar squared as 42, so the variance is 42 over 6, which is 7. The standard deviation is the square root of 7, about 2.65 or roughly £265, and notice it's back in the original units, unlike the variance. There's a small but important choice here. Dividing the sum of squares by n gives the population standard deviation, when your data is the whole set. Dividing instead by n minus 1 gives the sample standard deviation, used when your data is a sample you're using to estimate a bigger population. For large E, the two barely differ, but always state which you're doing, and at this level, dividing by n is the usual convention. When data comes as classes with frequencies, we don't have individual values, so we use each class midpoint as x. The standard deviation is the square root of the quantity sum of fx squared over sum of f minus the quantity sum of fx over sum of f, all squared. That second bracket, sum of fx over sum of f, is just the estimated mean, and sum of fx squared over sum of f is the mean of the squares. In practice, we build columns for fx and fx squared and total them. 4 steps once more. Find the midpoint x of each class. Multiply to get fx, then multiply again for fx squared, class by class. Total up the sum of f, the sum of fx, and the sum of fx squared. Then apply the formula, variance equals sum of fx squared over sum of f minus the mean squared, and square root it. Here's a grouped set, 5 classes with a total frequency, sum of f of 40. The estimated mean is the sum of fx over sum of f. That's 1010 over 40, which is 25.25. The sum of fx squared is 3600, so the mean of the squares is 3600 over 40, which is 765. The variance is 765 minus 25.25 squared, that's 765 minus 637.56, giving 127.44, and the standard deviation is the square root of 127.44, about 11.29. So, how do we read a standard deviation? A small one means the values cluster tightly around the mean, so the data is consistent, while a large one means they're widely spread and variable. Because it's in the same units as the data, it's genuinely easy to interpret, and it lets us compare the consistency of two data sets that share a similar mean. It's also the building block for the normal distribution we're about to meet. Picture two machines filling 500-gram bags, both averaging exactly 500 grams, but machine A has a standard deviation of 4 grams, and machine B one of 12 grams. On the mean alone, they look identical. But machine A's small spread means its bags are beautifully consistent, whereas machine B's larger spread means they vary far more. For quality control, you'd pick machine A every time, which shows exactly why the mean alone isn't enough. Spread matters too. The normal distribution is that famous symmetric, bell-shaped curve. Being symmetric about its center, its mean, median, and mode all sit in the same place. The total area under the curve is 1, or 100% of the data, which is what lets us read probabilities off it. And the tails stretch out forever, getting ever closer to the axis without ever quite touching it. The whole thing is pinned down by just two numbers, the mean and the standard deviation. Those two numbers have names. The mean, mu, fixes where the center of the curve sits along the axis. The standard deviation, sigma, fixes how wide it is. A small sigma gives a tall, narrow curve, a large sigma, a short, wide one. Changing mu just slides the whole curve left or right without altering its shape. So every normal distribution is completely described once you know its mu and its sigma. There's a lovely shortcut called the empirical rule. About 68% of the data lies within one standard deviation of the mean. About 95% lies within two standard deviations, and about 99.7% lies within 3. That 68, 95, 99.7 pattern holds for every normal distribution, and it gives you a quick feel for just how unusual a particular value is. Plenty of real measurements are close to normal. Adult heights, birth weights, and blood pressure all follow that bell shape. IQ scores are deliberately designed to be normal, with a mean of 100 and a standard deviation of 15. And measurement and manufacturing errors tend to cluster normally around a target value, which is why the Office for National Statistics leans on the normal model when analyzing so much national data. Here's the snag. There are infinitely many normal curves, one for every mu and sigma, so we convert them all to a single standard one. The standard normal distribution has a mean of 0 and a standard deviation of 1. We convert any value with z equals x minus mo over sigma. That z-score simply tells you how many standard deviations x sits above or below the mean. And once we have z, we can look probabilities up in the standard normal table. Reading the table is a 4-step habit. Standardize, converting x to z with z equals x minus mu over sigma. Read off phi of z, which gives the area to the left of z. Adjust for the tail you want. So for the probability that capital X is greater than x, you use 1 minus phi of z, and for a range, you subtract two areas. Then state your answer as a percentage or a proportion. Let's model adult male heights as normal with mu equals 175 centimeters and sigma equals 7 centimeters, and find the probability a man is shorter than 182 centimeters. We standardize z equals 182 minus 175 over 7, that's 7 over 7, which is exactly 1.0. From the table, phi of 1.0 is 0.8413, so about 84.1% of men are shorter than 182 centimeters. Same heights, mu 175 and sigma 7, but now the probability a man is taller than 189 centimeters. Standardizing, z equals 189 minus 125 over 7, that's 14 over 7, which is 2.0. Phi of 2.0 is 0.9772, but that's the area to the left, so the probability of being above is 1 minus 0.9772, which is 0.0228. So only about 2.3% of men are taller than 189 centimeters, and for any upper tail like this, you take 1 minus phi of z. Now arrange the percentage of men between 175 and 182 centimeters, same mu and sigma. The lower bound, 175, standardizes to z equals 0 and phi of 0 is 0.5000. The upper bound, 182, gives z equals 1.0 and phi of 1.0 is 0.84113. So the probability of being between them is phi of 1.0 minus phi of 0. That's 0.8413 minus 0.5000, which is 0.3413, about 34.1%. And that fits the empirical rule nicely. It's half of the central 68%, the bit just above the mean. Let's demystify that table. It gives phi of z the area to the left of each z score. Phi of 0 is 0.5000, which just confirms the curve is symmetric about the mean. Phi of 1 is 0.8413 and phi of 2 is 0.9772, and those tie straight back to the 68 and 95% rules. For a negative z, you use symmetry. Phi of minus z equals 1 minus phi of z, and honestly, those few values crack most simple normal problems. Step back and see why all this counts. The standard deviation and the normal model together let us judge how typical or how unusual any value really is, turning raw data into probabilities and then into informed decisions. Businesses use them for quality control, setting tolerances and weighing risk. And bodies like the Office for National Statistics use them to analyze national data and report the uncertainty around it. And the little formula z equals x minus mu over sigma is the bridge from any normal distribution to that one standard table. Let's tie the whole outcome together. The standard deviation measures the average spread from the mean using every value, and it's the square root of the variance. For ungrouped data, it's the square root of the sum of x minus x bar squared over n. And our worked example gave the square root of 7, about 2.65. For grouped data, we use midpoints, and ours gave 11.29. The normal distribution is symmetric and bell-shaped, set by mu and sigma with the 68, 95, 99.7 rule, and we standardize with z equals x minus mu over sigma, then read phi of z from the table to find probabilities. And that draws this outcome, and the whole unit, to a close. To reinforce it, Rowntree Statistics Without Tears gives a gentle account of spread and the bell curve, while Crawshaw and Chambers sets out the standard deviation and normal table work in full. The Royal Statistical Society's Significance magazine shows the normal model at work in real analysis, and the Office for National Statistics site is full of national data that follows these patterns. Corbett Maths and BBC Bitesize have clear worked examples on standard deviation and z-scores, and it's all waiting on the Moodle for this unit.